Hi, today I'm at a conference at Maine West, but I still wanted to get started talking about angled projectiles. And we're going to see that angled projectiles aren't really a whole lot different than what we've already talked about with horizontal projectiles and what we talked about in the last unit on objects rising and falling in air. To review, if you just drop something from a height, let's say a cannonball, when you drop it, its initial horizontal velocity is going to be 0, and its initial vertical velocity is going to be 0. But according to Galileo, all objects will accelerate downwards at 10 meters per second squared, or g, which means that the height the object falls is going to be equal to 1/2 gt squared, and the time it takes to fall is going to be equal to our old friend, the square root of 2h over g. Again, these are just a review of kinematics equations. When a projectile is fired with some horizontal velocity from a height, the only difference is the horizontal velocity now is not 0 meters per second, but it's some other value. The vertical velocity still starts out at 0 meters per second. The acceleration is still 10 meters per second squared downward, and the height and time equations are exactly the same. But now, because the object is moving horizontally, the horizontal distance it travels, or its range, is going to be equal to VH times the time. So at any point in time, a projectile's instantaneous velocity has a vertical component that exhibits free fall acceleration, just like any object that falls, and it has a horizontal component that's going to be constant velocity. At any point in time, the total or resultant velocity is going to be the sum of the horizontal and vertical components. So you can see that at this point, when it first starts out, it has a horizontal velocity of 20 meters per second and no vertical velocity. But then, 1 second later, it still has a horizontal velocity of 20 meters per second, but now it has a vertical velocity of about 10 meters per second. After 2 seconds, it still has a horizontal velocity of 20 meters per second, but it has a vertical velocity of about 20 meters per second. Again, every second it's going to gain 10 meters per second in the vertical direction, but stay 20 meters per second in the horizontal direction. Even though these components are independent of each other, the vertical and horizontal, they both have to act for the same amount of time, which is determined by the vertical distance traveled. Again, even though the vertical and horizontal motions occur for the same time, they're controlled by the vertical motion. An object will only move horizontally as long as it's moving vertically. Once it hits the ground, it stops. As is always the case, the vertical velocity of any object at its highest point is always going to be 0. We've talked about that over and over again, that anytime something changes direction, it's going from a positive velocity to a negative velocity, or a negative velocity to a positive velocity, and so its velocity has to be 0, which means, again, at the highest point, anything's velocity is always 0. So any object that's going up has to start out with some vertical velocity so that it can slow down to 0. Remember that any object that's going up has to slow down. And so when it first leaves your hand or leaves whatever, it has to have some velocity so that by the time it gets to the top, it can have a velocity of 0. So again, any object that is thrown or shot up into the air must have some initial vertical velocity. There's no horizontal component since it's not moving horizontally, so the only component is vertical. The time going up and the time coming down have to be exactly the same, as long as it lands in the same spot. And for all purposes, that's pretty much the cases that we're going to deal with. Since the acceleration is delta v over t, it's just the definition of acceleration, we rearrange that to time is equal to the change in velocity divided by g. Since the object starts going up with a velocity of vv, its vertical velocity, and at the top of its path it has a velocity of 0, when it comes back down to the same height, its velocity is going to be negative VV. This is something we've talked about before. So the change in velocity is going to be 2VV, which means the time is going to be 2VV over G. And so the time for anything that's going up is not the square root of 2h over G. Because it's two-way motion, the time is going to be 2VV over G. This is an equation we've used before, and we're going to be using quite a bit more. The height going up and coming down is also the same. The distance up is the same as the distance down. That goes back to when we were talking about reaction time and hang time. Again, the down trip is always easier to deal with, and so the final velocity squared is equal to the initial velocity squared plus 2gh, one of our kinematics equations. Since the initial velocity is 0 and the final velocity is simply vf, or actually vv, then vv squared is equal to 2gh. The height, when we rearrange, is going to be equal to vv squared over 2g. So the height that the projectile rises to depends on its initial vertical velocity, vv squared, then divided by 2g. An angled projectile is any projectile that's launched at an angle from the horizontal at some initial velocity. Since they go up and forward, there has to be some vertical and horizontal components to that initial velocity. So instead of just having a vertical component, again, a projectile has a vertical and a horizontal component. The vertical component is still free fall acceleration, and the horizontal component is still constant velocity. So that really doesn't change. The only thing we add to it is the horizontal component. As the projectile goes up or rises, the vertical component gets smaller until at the top it's going to be 0. Because again, at the highest point, anything's vertical velocity has to be 0. The horizontal component, because it's constant velocity, remains constant. The horizontal and vertical components of the initial velocity form a right triangle. You can see that in the diagram here. So their magnitudes can be calculated using trig functions. It's important to keep track of our variables here because it can get confusing. VI is always the initial velocity. It has nothing to do with direction. It's whatever the velocity is. Vertical velocity, or the initial vertical velocity, we call VV. And so it's a component of the initial velocity. VH is the horizontal velocity. And again, it's just a component of the initial velocity. And you can see we've got a right triangle here with the hypotenuse being the initial velocity at some angle theta from the horizontal. Because it's a right triangle, the vertical component is the opposite side of the triangle. So the vertical component VV is going to be equal to VI times the sine of theta. Again, that's kind of an equation we've been using over and over again. The horizontal component, on the other hand, is the adjacent side of the triangle. So the horizontal component, VH, is going to be equal to the initial velocity times the cosine of the angle. The time of flight is still determined by the vertical motion, and that motion is up and down, so the time of flight is going to be, T is going to be equal to 2VV over G. Again, it's the same equation we had before, when we were just tossing something into the air. The maximum height the projectile reaches is also determined by the vertical motion, and that height is going to be VV squared divided by 2G. Again, exactly the same equation as we had for non-projectile motion. These equations, again, are the same for angled projectiles and for objects thrown into the air. The only difference is that there's a horizontal component, but that horizontal component is constant velocity. So the range, the horizontal distance the object goes, is still going to be the horizontal velocity, VH, times whatever the time is. And again, just to reinforce, that time is going to be determined by the vertical motion. So this table kind of summarizes everything we've been talking about. And again, these equations should be in your notes already. If not, the ones for angled projectiles are on the handout you either have already picked up or will pick up. The important thing to remember about these is that the equations for horizontal projectiles and angled projectiles, with the exception of range, are not the same. So when we approach problems involving horizontal and angled projectiles, one of the first steps is going to be determine which type of projectile is it. Is it a horizontal projectile just fired from a height, or is it an angled projectile? And that's going to determine which equations you use. Notice also that for horizontal projectiles, the horizontal velocity is the initial velocity because the vertical component starts out as 0. For an angled projectile, however, you have a horizontal component and a vertical component right at the beginning. And that's usually the first thing you have to determine is what are those components. And we'll be getting some practice with that later on. Those are an awful lot of equations to remember. So the range equation is one equation that combines all of these equations together to find the range given only the initial velocity and the angle. And so it's kind of a shortcut. Instead of having to work through all these things, you just start with the initial velocity and the angle. Okay, so based on our equations, time is equal to range divided by VH. Time is also equal to 2 times VV divided by G. Since those times have to be exactly the same, we can use the reflexive property and combine them together, and so range divided by VH is equal to 2VV over G. And again, these steps really aren't important, it's just to show you how this equation comes about. So we can rearrange that equation a little bit, and so the range is equal to 2 times VV times VH divided by G. We substitute our definitions for VV and VH using the trig functions, and so we have the range is equal to 2 times VI times the sine of theta, which is VV, times VI times cosine theta, which is VH, divided by G. So we start with that equation again, and then we can do some regrouping. We combine our VI terms together, we move the 2 over, and we have VI squared times the quantity of 2 sine theta cosine theta divided by G. So we just regroup there. We could leave it like this because we have the initial velocity, we have the angle, and we know what G is, but that's still an awful lot of things to put into the calculator. If you are a fan of trig, you've already had trig in math, you should know this. This is one of the great trig identities. It turns out that 2 sine theta cosine theta is always equal to the sine of 2 theta. I'd like to thank Mr. Dan Wilson, who was my math teacher here at Maine East, for pounding that into my head. And so this is one of the reasons why we kind of learn those identities, because it makes life a little bit useful for us. So we can substitute that back in, and we have, ta-da, the range equation. The range equation simply says that the range of an angled projectile is going to be equal to VI squared, its initial velocity squared, times the sine of 2 times theta divided by G. And G is going to be 10. And so that's kind of a shortcut method of finding the range. The only problem with using this equation is you can't use it to answer questions like how much time is the projectile going to be in the air, or what's the maximum height that it's going to reach. This is just a shortcut method for finding range. But more times than not, that's really what you're asked for, is what is the range of the projectile. And in most practical applications, that's also what you're looking for, is what is the range. So the range equation does become useful. So angled projectiles are probably one of the physics concepts that most applies to our daily lives. Anytime you hit a ball, kick a ball, throw a ball, shoot something, whether it's an arrow or whatever, throw your body over a bar, like a high jumper, hurdler, pole vaulter, become a long jumper, triple jumper, whatever, you are using the concept